5.3, the basic concepts, right? But here we have a very big concept of HL level. So I'm going to discuss that. Let me open and share the screen with you. Sorry for inconvenience, but I was working on those notes, so just I realized that I must share these with you before you forget about them. Okay, here is that. So now do you see the screen?
Mm,
Is it
yeah.
now, is it visible?
Yes, sir.
Okay, so here, as I told you, that this capacitance topic is also involved in some of the areas, which is 5.1 and 5.2, 3, and 4. So here I would have its extended discussion. Okay, and we will talk about capacitance, dielectric, then capacitors and series, and capacitors in parallel, and then resistors and capacitors in the circuits, RC, time constants, and all that stuff will be discussed over here. So when I say that what a capacitance is, so capacitance is basically the ability of a capacitor to store the charge, right? So here we have a lot of areas to be discussed, and these all are the materials which are available in your book, data booklet, right? Your equations are there, and that equation is your C is equals to Q by V, right? That is the capacitance equation, defining equation. Then the capacitance of parallel capacitors, then capacitance of series capacitors, then capacitance of a capacitor with a dielectric material, and area and distance or separation between the plates. Then we have to talk about the energy stored in the capacitors. Then we will talk about RC time constant, then charging, discharging, current, and voltages and charge. So these all are basically capacitors. Is it clear?
Okay. Yeah.
Okay. So actually, you have been given a lot of information about your capacitance in your booklet. So very few areas are there in which you would have some sort of memorization. Otherwise, rest all is fine. So if I say that we talk about the major area, okay, major area of the that is the international mindset. Okay, leave that international mindset because we have just mindset to attempt the paper. Here is that. So when you talk about the capacitors, what type of capacitors do you see in your daily life? There are so many capacitors. So all these are capacitors.
Yeah.
Okay, na? Okay,
Yeah.
so I can say I can say that a capacitor is an electric device or electrostatic device, basically, or electronic device. What does it do? It stores the energy. So here is its internal structure, and then there are some sort of electrodes. You can say electrodes means these are the plates which are being used. Then when we've talked about the capacitors, the basic structure of the capacitor was something like something like that. The capacitor was having two parallel plates. Let me just go through or show you the topic of your 5.3 from here. That will make you I mean, you will have a link of your topic with this one. Okay,
Okay.
so here we go. We have the capacitors over here. Here is that. Okay, so is it visible to you?
Yes.
Okay, so a capacitor is defined as the arrangement of two conductors separated by an insulating material. We call that as a capacitor. And then capacitance is defined as the charge per unit voltage is stored on the capacitor, or you can say the voltage is the ratio of charge to the potential difference. Okay, ratio of charge to the potential difference. So I can say that is the capacitance. So here C is equals to Q by V, where C is the capacitance, its unit is farad, Q is the charge, its unit is coulomb, and V is the voltages, its unit is volt. Here is that basic concept of a capacitor. That capacitor consists of two conducting plates with certain area and separation between them. Then we have some insulating material inside. So symbol of the capacitor is this. You believe this thing that sorry, I believe that you know that. Okay,
Yeah.
here we go, that if we have a concept of a parallel plate capacitor, then plate capacitor, the capacitance of the parallel plate capacitor depends upon several factors, which is basically your area and separation between the plates. And the capacitance is directly proportional to area, and capacitance is inversely proportional to the separation between the plates. So if I say that I have a capacitor with a certain area of the plates and I have the separation between them, so as the separation increases, what will happen? The capacitance decreases, capacitance of the capacitor decreases. Similarly, we have a concept of dielectric over here. Dielectric is basically that material which is kept in between the plates to separate out the charges. Okay, to keep the charges
Yeah.
separated. Okay, so here is that basic concept, and after that, I will go to the extended level, and then the energy stored in the capacitor can be calculated by 1 by 2 CV square. You know, these all are this all is the stuff which is given to you in your data booklet. And then we have series and parallel combination of the capacitors. That capacitors are connected in series and then they can be connected in parallel, and to get either increased capacitance or decreased capacitance. So that all is, I believe that it is clear to you, right? Should I
Yeah.
consider this, that this area is fine, or you are fine with this area?
Yeah.
So after this, I'm coming to this 11.3, that a capacitor consists of two parallel plates, right? And then that is called parallel plate capacitor. Then on the basis of a dielectric, we usually call it the electrolyte capacitors. They are having very high capacity of the capacity than that of the parallel plate capacitors. Here is the basic definition of capacitance. That capacitance C, define capacitance C to the charge per unit volt V of the capacitor, or the ability of the capacitor to store the charge, right? Or to store the energy. So its unit is sorry, its formula is C is equals to Q by V. What is its formula? C by V, and sorry, Q by V. And this is basically its unit is farad here. And let's say if I have 1.5 volt cell connected to a 275 microfarad capacitor, right? How much charge will be stored on that? So we will use this equation, very simple. Q is equal to CV. So C is the subject over here. So C is equal to Q by V. Sorry, Q is the subject over here. C is given to me. Q is the subject. Q is equal to CV. I will make it Q is equal to CV, and C is given to me. Capacitance is given. Then V is given, and I will get this much charge will be stored on that. So this is actually the basic concept. Now we have the concept of capacitors in parallel. When we have capacitors in parallel, you know what happens? All the capacitors are connected with each other in such a way that the identical plates of the capacitors are connected with each other. Or here is the battery. So sometimes we have a problem with this, that the battery and capacitors have similar symbols, but capacitor has equal length bars and battery has a smaller and a larger one. So when capacitors are connected in such a way that one plate of each capacitor is connected with positive terminal of the battery, and other plate of each capacitor is connected with the negative terminal of the battery, that is called your parallel combination, right? Is it clear?
Yeah.
Okay, so here we go. In parallel plate capacitors, this is one of the example which is called a variable capacitor, which is it has many parallel plates, and it is usually called a gang capacitor. It is basically used to tune the radios in manually in the old times. Okay,
Okay.
so I can say that is in parallel combination, voltages remain same. You believe this thing that what happens? The voltages remains unchanged. So I can say that V is equals to V1 plus V2. What is the situation over here? That V is equals to V1 plus V2. So this is
Mm.
basically the equation you have to remember. Then, as you know that Q is equals to CV. Q is equals to CV. It means Q1 will be equals to C1 V1 and Q2 will be equals to C2 V2. So if apply this all on the equation CV, yani V is equals to V1 is equal to V2. So the main area or the master equation is this one. This is the master equation in the parallel combination. Q is equals to Q1 plus Q2. So charge is distributed among the capacitors. So we can consider, we say that charge is sum of all the charges. Total charge is equal to sum of individual charges. So Q is equal to Q1 plus Q2. You have to remember that. So Q is equal to CV, Q1 is equal to C1 V1, Q2 is equal to C2 V2, and as I told you in this equation that V is same. So just keep this V common and cancel it. So you will say C1 is equal to C1 plus C2. So in parallel combination, just capacitances are added. Simply, what do you say? That in parallel combination, your capacitances are added,
Yeah.
right? Charges are added and capacitances are added, but voltages are unchanged. Okay,
Okay.
ये बात समझ आ गई?
Yeah. G.
Okay, good. Now we will talk about the some sort of examples over there. For example, the same capacitor, 1.5 volt cell is connected to 275 microfarad capacitor and a 38 microfarad capacitor. They are connected in parallel with each other. Here are they. Calculate the combined capacitance. So you have to add them both. So it would become 275 plus 38. I mean 303 exponent minus 6 farad. So how much charge would be stored, or how much charge has the battery placed on the capacitors? So what equation will you use? You will use Q is equal to CV. You have to find Q. C is your 303 exponent minus 6. I mean 303 microfarad, and your V is 1.5. So overall, your answer is 450 microcoulomb. Sorry, 455 microcoulomb. So each charge would have a different charge on it. Here we go. Whether I can say that if I calculate Q1, so Q1, C1 V1. Okay, C1 V1. So I can say that capacitor number one, this capacitor, whose capacitance is 275 into 10 raised power minus 6, it would have a charge equals to. Do you have a calculator? Should
Yes.
I multiply this? Yes. So just go that. When my kids take the phone, they just change the setup of the phone. I don't get any app in order. So
Uh,
I don't know where is my calculator.
4.125 times 10 to the power of
Okay,
negative
4.125 exponent minus 6 or
4.
minus 7,
4.
minus
Minus 4.
4 coulomb. Yes, this is a charge stored on your capacitor number one. I mean 275 microfarad wala capacitor, and then I can set that Q2 is equals to C2 into V2. So C is 38 microfarad, so 38 into 10 raised power minus 6, and voltages are 1.5. So what will be the answer?
Uh, should be
38 and half of
5.7.
38 is 29. Huh?
5.7 times 10 to the power of negative 5.
Yes. So this is a total. This is the charge individually stored on each plate of the capacitor. I mean each capacitor. So as you now, Q is equal to Q1 plus Q2. So if I add them all, 4.125 into 10 raised power minus 4 plus 5.7 exponent minus 5. So what would be your answer?
My answer would be
It should be, it should be this one.
4.
Mhm. Is it?
One second. Huh.
Yeah. Okay.
Mm,
It should be
no.
no.
I'm getting 4.695
Okay. 4.695 mean 4.7 into 10 raised power
into 10 raised power negative 4.
negative 4.
Yeah.
Okay. So probably 275 microcoulomb into 1.5 volts. It would be the charge on this capacitor, and C2 is 38 microfarad, and it should be multiplied by V2 because that is same. So it is not possible. The answer should be same. Because listen, as I told you, that what is the total according to, so it is basically the denial of theory. We say that the total charge is sum of individual charges. Do we?
Yeah.
So total charge I got in that calculation. What was the total charge? Total charge was 455 into 10 is bar minus 6 coulomb. Okay. So individual charge I got 4 point. Okay. Can you write this as 0.41 into 10 raised power? Sorry, very good. 41.3 into 10 raised power minus 5 plus 5.7 into 10 raised power minus 5. So add them both. What do you get? It was 7 plus 3 0, 5 plus 1 6, and 4. Yes, 46.0 into 10 raised power minus 5. No, no, no. We are getting the same answer. Yeah. What are you doing, boy? Okay, so it is 46.0 exponent minus 5. So that means 4.6 into 10 raised power minus, sorry, 466 or something like that. Okay, wait. 4.6 into 10 raised power minus 5. Just keep it over here and convert this into 4.5. So if I use that 4.55
20
into 10 raised power minus 5.
minus
So
minus 8.
this one minus 8?
Wait.
Minus 8.
No. Wait.
We are
Yeah.
making some mistake in calculation. That's it. Otherwise, no. Because here it is 460 into 10, 4. No. Here we made a mistake. Now it is 46 exponent minus 5 now. So if I want to make it 4 minus 6, so I would like that 460 into 10 raised power minus 6. Is it clear?
It would be 4.55 times 10 to the power of minus 4. So if it is
Yes.
minus,
No, just keep it same. 455 into 10 raised power minus 6, that is fine. And if I check this one, it is almost same 460 exponent minus 6. Okay,
this it's approximately the same.
approximately the same because we have rounded off the values now. One, two, three,
Yeah.
one, two, three places. Is it clear?
Yeah. Yes, sir.
So this is what, that if you are having individual charges, you must know how to find out this separate charges on on the capacitors. Okay, should I move on
Okay.
to next?
Yes.
Capacitance in series. Okay,
Yeah.
so when we have capacitance in series, actually at that time we can have that is, oh, where I, why is it stuck? Do you see the screen? Stuck
Yeah.
to nahi hai. Okay, okay,
Mm,
yes, that's fine. It is now released. Capacitance in series means we can connect the capacitors in series in such a way that end of one capacitor should be connected with the end of the other capacitor. I mean, positive with R. You can say one plate, A, and this is plate B, then this is plate A and this is plate B. So they are connected end to end. When we connect them by end to end, that combination is called your series combination, right? In series combination, what is beauty of series combination? That charge remains unchanged. Charge would be same, whatever the actually. I would like to make you clear in such a way. This is plate 1 of a capacitor, this is plate 2 of a the same capacitor, this is plate 1 of the second capacitor, this is plate 2 of the second capacitor, and these capacitors are connected with each other in this way. So according to electrostatic charge, our concept of electrostatic, do you know why the charge is accumulated on this? Electrostatic induction takes place. So if we have positive charge on this plate, it would induce an equivalent opposite charge on this plate. Similarly, this is your capacitors of capacitance C1, this is your capacitor of capacitance C2, and due to this negative charge, there would be an equivalent opposite positive charge on this one, and due to that, a negative charge would be induced on this plate. So overall, for example, here you are able to produce 4Q positive, the same would be 4Q negative on this plate. Okay,
yes.
and similarly the same would be over here, 4Q positive over here and 4Q negative on this side. So whatever the charge is stored on plate 1 or accumulated on plate 1, the same goes to the last plate in series. So in series, charge does not change. Remember this thing. Is it clear?
Yeah.
Okay, okay, is it clear to you? So
Yes,
what
sir.
changes then? Recording all done about, yeah. What changes then? The voltage is changed. Voltage is in series, potential divider rule rule is applied, and voltages across each plate of the capacitor is different. So we can say that V is equals to V1 plus V2. So if I just apply this is as a master equation, because this is my master equation. V is equals to, because V is equals to Q by C. Is it? Are you getting it? V is equals to Q by C, right?
Yeah.
Then V1 is equal to Q1 divided by C1, and V2 is equal to Q2 divided by C2. So I would just plug in all those values. Instead of V, I plugged as Q by C. Instead of V1, I plugged Q1 divided by C1 plus Q2 divided by C2. And as Q is same, so Q would be gone on from both sides. It would be basically, we can take it common and cancel it. As a result, you are having this number, 1 upon C equivalent, 1 upon C is equals to 1 upon C1 plus 1 upon C2 plus 1 upon C3. Is this clear to you?
Yes.
So this is also a sort of equation. I will give you another format of this equation. That equation is, you can write this equation over here for two capacitors. This is just for two capacitors. What I'm going to write now, this is just for two capacitors. That equation is C equivalent equals to C1 into C2 divided by C1 plus C2. Okay, is it clear?
Yes.
It is called product over some formula as we use in series. Na, just let me plug in one page, empty page over here. Okay, so that is, if I have two capacitors, one capacitor, one is uh, of capacitance C1 and capacitor 2 is of capacitance C2, and I want to find out the total capacitance. I will take reciprocal, I mean I will take LCM of this. It would be C1 into C2, and at the top it would become C2 plus C1, and here it is 1 upon C equivalent. So just solve it. It is actually C1 plus C2 divided by C1 times C2, that is equal to 1 upon C equivalent. Your target is not 1 upon C equivalent. What is your target? Your target is C equivalent, I mean total capacitance. So I have taken reciprocal of this. So I have to reciprocate that one as well. It would be C1 into C2 divided by C1 plus C2. Is this clear to you?
Yes.
So I will refer, or I will prefer to write this equation when there are two capacitors, not that one, the 1 upon C1. Is it clear to you?
Yes.
Okay. So here is an example. The same question goes on that when we are going to have the capacitance of 275 a voltage of 150, then what would be the charge stored on that? So we just calculated the equivalent capacitance. Wherever you do, just find the equivalent capacitance. That is 1 upon. Uh, when you reach to this stage, this is very important. If you follow this method, when you reach to this stage, just take reciprocal. So your final answer is this one:
Yeah.
3.34 into 10 is power minus 5. So after this, how much charge has the battery placed on each capacitor? So because charge is same, so charge for each capacitor would be same, so it would be 3.34 exponent minus 5 simply. But what about the voltages across each capacitor? So v1 is equal to q1 divided by c1, okay, and v2 is equal to q2 divided by c2. So if I follow that, so charge will be, here we have calculated it was 3.34. So when we applied q is equal to c, we go through this line. So you got that by using capacitance and voltages, you got 5.1 into 10 is power minus 5 coulomb. So this is used in both the cases, divided by 275 exponent minus 6, you got 0.18 volt. And for the next, or for the second one, whose capacitance is 38 microfarad, you got 1.32 into 10 is power 1.32 volts. So simply speaking, if you add them both, what voltages should you get?
1.53.
Yes, you should get 1.5 approximately, because according to the rule, in series combination, voltages across this one and voltages across this one, they are equal to the voltages applied. So applied voltages are how much?
Apply
Is
voltage
it?
1.5.
Yes, so we are getting almost 1.5.
Yeah.
Is it clear to you?
Yes, sir.
Very good. Now, here we go. That what is the dielectric material? As I told you, that here we are two wires, one is red and one is black, and the copper inside them, and these two wires are kept at a distance from each other. So these plates, or these wires, would act just like your capacitors. Okay.
Yeah.
Are you getting it? So the capacitor
Yes.
consists of two conductors and they are separated by the voltages across them. So if we say that these are now the plates with, I mean, these are the wires with a bigger area. We have just put these discs along the wires to increase their area. Or in simple words, what can we do? We can flat these wires by hammering them. Okay, by hammering them, they will behave like a capacitor. Are you getting
Yep.
it?
Yes, sir.
Okay. So if I say that this is the same concept as I had delivered to you, that these two plates are at a distance d from each other and they have a specific area A of cross section, and that area would be definitely depending upon some sort of the dimensions of that. So don't overlook this. Increase the area over which the charge can be stored. So if you want to keep more charges on the plates, so what do you need? You have to make this area as a bigger one. I mean, it is just like your plants. If you want to grow more plants, you have to increase the area of the soil, area of the field, isn't it? So
Yes, sir.
that there would be an equal and opposite charges would be accumulated on the other plate. So simply speaking, if you have more positives, you will have more negative. And how to get more positive? If you have more area, you will get more positive. Right? Is this clear to you?
Yes, sir.
Oh, very good. The next is, if we have to decrease the distance between the plates, the distance between the plates must be kept as small as possible. There is a reason behind that, and the reason is very simple. But if you are not able to understand that, you will not be you will not get it. Why there is a charge on one plate, that is due to the positive terminal of the battery. But why there is a charge on the other plate? Because these electrons are this plate actually
Attracted.
repels the electron. Yes, attraction. Yes, you can say. I will draw. I will draw a diagram over here. I will try my best to draw as clear diagram as possible.
Mhm.
Wait. I have a diagram over here. So why don't I use that one available? So I should use that one to save my time. So here is that. You know, if this plate is connected to the positive terminal, sorry, negative terminal, all electrons would accumulate over here. Okay,
Yeah.
and due to that, there would be an astonishing effect on the other plate. What is that effect? That effect is they will these electrons will repel the electrons of the nearby plate. There are definitely electrons. So these all electrons would be repelled, and these electrons would be driven through this wire. They would be driven through this wire towards battery. As a result, there are appearing some positive charges. We are having positive charges over here. So this is what that we make clear, that the energy is stored due to repulsion of these charges from one plate to another plate. To push these charges from one plate to another plate. So if these plates would be kept closer, there would be more electrostatic force. You know this thing, that the electrostatic force is too thick, yeah. Okay, so when there are electrostatic forces, you know that they are 1 upon 4 pi epsilon naught q. Q1 Q2 divided by R square. Do you know this equation? So if
Yeah.
this distance will be smaller enough, this is that distance. If it will be smaller enough, then more force of repulsion would be available and more charges would be pushed down. So this is why we keep the distance smaller and we keep the area larger. Is it clear?
Yeah.
So here is that concept of the pushing the charges. So this is what, this is the dielectric material. So when we keep the dielectric material in between, dielectric material means any insulator positive and negative, positive and negative charges accumulating on it. Here is that concept. Yes, here is that. So that when you will place this dielectric in between the plates, that dielectric will basically have the electric field lines on it, right? This plate is negative, so what will happen, there would be an electric field. Electric field means from positive to the negative field, negative plate. Okay,
Yeah.
and due to that, what will happen, there would be a force of attraction between them, and then the energy would be stored over there. So that energy is stored, I can say, here is that equation, that the capacitance of a charge or capacitance of a capacitor is, yeah, this is that equation. I have referred all of that over here, so it is in available for your convenience. So capacitance is directly proportional to area of the plates. Capacitance is directly proportional to area of the plate, and capacitance is inversely proportional to the separation between the plates. So when I combine these two variables, I get capacitance is equals to epsilon naught A upon D, where epsilon is, what is epsilon? Epsilon is your dielectric
Permittivity.
constant. Yeah,
Oh,
permittivity of free space. Okay,
yeah.
is it clear?
Yes, sir.
Okay, very good. So its value is, for air or vacuum, it is 8.85 into 10 is power minus 12 farad per meter. For 1 meter distance, we can produce the capacitance of 8.85 into 10 is power minus 12. Right now, here we go. That if we have some other material, uh, then that of the air are insulating air, so its capacitance is increased. Okay, so electric field strength has a ratio of that. So E naught divided by E is basically the ratio. So I can say simply, I will go directly towards that. From Q is equals to CV, right? And V is equals to E by D. We can say that, because here, from this equation, your V is equals to Q by C, and from this equation, your V is equals to E times D. So these two are combined over here in this format, right? From here, we get that now your C is equals to Q divided by ED, right? From this equation, this tells that smaller the electric field, then larger the capacitance will be. Is it clear to you?
Yes, sir.
Yes. Okay.
Yes.
So here we can simply say that area can be calculated in different ways, right? Your capacitance have this equation, and you can calculate the separation. Whatever you are being asked, it can be calculated. So should I require this all to calculate, or you just look at this slide and let me know? Yeah, there is one very important thing. Yes, 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 yes. Here is the concept of relative permittivity, right?
Yeah.
The relative permittivity of the material is little of that material is 4 times the permittivity of the free space. Okay, it means that if we increase the permittivity of free space, if we place material inside, then what will happen? the capacitance of the capacitor would be increased. That's why we plug in some dielectric material inside. So here is that concept that if we will not use any material, without material, capacitance would be 4 times less. But if we will plug in some material, the capacitance would be increased. Okay.
Yeah.
So here is the concept now, the concept of energy stored. In this slide, this is another very important slide, right? The energy stored in the capacitor. So what about the इरफान साहब को कॉल करके बता दो कि I have a class, so आपको कन्वे करना है जो भी बात बोलनी है आपको बता दो. From relationship of C is equals to Q by V, we can write that V is equals to 1 upon, I mean, I have written that in over here, 1 upon CV times 1 upon C times Q. So forget about that. Just consider that when we have a relation between Q and V, are they not directly proportional to each other? V is equals to,
Yeah.
I mean, if I write this equation, Q is equals to C times V. So can I say that V is equals to Q by C? Can I say that?
Yeah.
Yes. So
Yeah.
if I just invert this, if I write V by Q, so can I get C?
Yeah.
So here we go. If we have V and Q graph, its gradient gives you capacitance. Okay? QV or VQ graphs gradient gives us capacitance. But it's, if we say that energy stored in the capacitor is Q times V, so Q and V will be multiplied with each other. It means that there is an area under the graph will give us the energy stored. So as I shown you, that gradient is equal to capacitance, but area is equal to energy stored in the capacitor. Okay. So energy stored in the capacitor. So what will be the area of this triangular portion? 1 by 2 base times height. So base is your Q and height is your V. So I can say that it is W is equals to 1 by 2 QV. Is it clear to you?
Yeah. Yes, sir.
So just replace the number Q is equals to CV, right? What to do? Just replace it. I mean to say that as you have written that E is equals to 1 by 2 QV, and as Q is equals to CV, just replace this Q with CV, and you will get another equation, that is 1 by 2 CV square. Okay?
Okay.
Is it
Okay.
clear to you?
Yes.
Okay. Okay. Here is, um, don't get scared. They are just having some firework to welcome the Eid in the other room.
Oh,
Okay.
I cannot hear it. I cannot
Okay.
hear it.
This is your childhood. You believe this thing.
Yeah.
Okay. दरवाजा बंद करके जाओ. Here is the capacitance equation, that 1 upon 2 QV or 1 upon 2 CV square. Okay. Will you
Okay.
be able to retain these equations?
Yeah, I think so.
Yeah.
Yeah.
Abdullah, just a minute. Let
Yeah.
me guide them.
Yeah.
Okay, actually, most of the time I used to take class in the upper floor, so they just enjoy their life at the ground floor, whatever they do, no restriction at all. But today I'm taking class on the same floor as the kids have. So
Yeah. Oh, yes.
Now they are restricted. Okay यार, अब वो एक कमरे में क्लास ले रहे हैं और दूसरे कमरे में हम कैसे बैठ सकते हैं खामोशी से?
Yeah.
I have four kids, so when there are two plus two, so they make a entire mess in the room. Okay, so is this clear, beta?
Yes, sir.
Okay, well done. Now come to some other aspect of this these solving problems involving the parallel plate capacitors. Just we will have a quick review and then I will go to the charging and discharging area. Two capacitors in circuit are fully charged to 1.5 volts. C2 is initially uncharged. What will be the electrical energy stored in C1? Here we go. Here is voltage is given to you, right? C2 is initially uncharged, right? This capacitor is not charged. C2 is this one. Here is your C2. Okay, what is the electrical energy stored in C1 and what is the charge on C1's plate? So how to solve that? We know that Q is equals to, or E is equals to 1 by 2 CV square. So if I solve that, I have solved that in the previous slide over there, that 1 upon CV square, because that is the same question, extended one. 1 upon CV square mean we got that we have capacitance of 275 microcoulomb and microfarad, and 1.5 is the voltages, so it gives you 3.09 into 10 to the power minus 4 joule. So that is the energy, so I'm going to use that energy. Now by using that Q is equal to CV, we would get capacitance. We will make C as a subject, right? Is it clear? You have to make C as a subject. C. So C is equals to what? Q
Subject.
divided by V.
It's
Yes,
to V,
270.
V divided Q. V divided by V.
Yes, yes, it would be. Yes, C would. Sorry. We have to find Q. Sorry, my bad. Q, and Q is equal to C into V. So C is 275 into 10 to the power minus 6, and V is 1.5. So you got this much charge stored on any one of the plate of this
Yeah.
capacitor, right?
Right.
And then this is basically the same question, but the next part, the capacitors are in parallel, so voltages of one are equals to voltage of two. So q1 divided by c1 is equals to q2 divided by c2. So q2 is, this is very important formula, you have to remember that or recall it, that q2 is actually c2 divided by c1, ratio of capacitances into charge. So I can say that from this concept, I would like to review that the conservation of charge is Q4.125 into 10 to the power minus 4. How did I get this? That because both the capacitors are in parallel, so both would have the different charge, and that charge was total charge is 4.125 into 10 to the power minus 4. It is the total charge, right? It is what?
Yeah.
Total charge.
Total.
So total charge will be divided among two charges. So if I add charge of 1 plus charge of 2, then I will get total charge. So I know that the total charge Q1 is to be, I mean, Q1 is over here, Q1 and plus Q2. Q2 is C1 divided by C2 into Q1. Now you got it? I have
Yes.
just replaced this equation. Check this one out. I have replaced this equation. The value of Q2 from here to make this equation as a one variable. So that equation has C2 divided by C1 because I know the capacitances, and then I would plug those values over here, and I will keep this charge out Q1, and I will get 1 plus ratio of capacitances. So Q1 is given to you. So Q1 is 3.62 into 10 to the power minus 4 coulomb. And now we believe that the total charge, here we go, Q2 is equals to 4.125 exponent minus 4. This was the total charge. This one minus Q2, no, sorry, minus Q1 plus Q2. So Q1 is 3.62 I got this number 5.01 10 power minus 5. Okay, so we can solve these type of questions from capacitors. Okay, is it clear to you?
Yes, sir.
So I'm going to move on because we will be getting slower if we will solve all of these papers one by one. So if you can solve these type of questions, fine. Otherwise, we will be back to the questions. So here we go. This was just ended up over here, solving problems till this point. So here is discharging the capacitors, right?
Yeah.
Charging capacitors. So when we have capacitors, as I told you that capacitors store the energy. So when store the energy, that process is called charging of capacitor, right? What do we call it? We call it capacitor, yani storage of energy of the capacitor. So for example, if we have a 1.5 volt battery and it is connected to a capacitor, then initially it would give some voltages to the capacitor, and that is of 275 microfarad capacitor, and it would be fully charged after some time t. Before the switch is closed, check this one out, the switch is open, so there is no voltages across, there would be no voltages across the capacitor. अच्छा अच्छा मैं आके देखता हूँ. I have a complaint cell as well over here. बाबा भैया ने भव्या को मारा है. So I have to
Okay.
figure out all those areas as well.
It's okay, sir.
Okay, now come back to the point here. These kids are very naughty. So capacitor is having voltage is V, then charge flows through that, or current flows through that, and capacitor is now start charging. So when we say that capacitor is getting charged, so it would have zero voltages initially,
Yeah.
okay? So there is no
Okay.
voltage at all at the capacitor. It does not have any voltage. Then what will we do? We will mean the charges would, we will close the switch from one plate to the other, and in this way it would work on the charges and energy will be stored on that. So finally, when all of the voltages would be, I mean, when it would behave just like an open switch. Remember this is very interesting thing, that why it is having all 1.5 volts across it, because here all that switch is closed. This is now behaving just like an open switch because it has all the positives over here and all the negatives over here, so they cannot jump over. So when they will not be able to jump over, there is no bridge in between. So here is just like an open switch. Okay, so when it is an open area, all of the voltage would be accumulated over there. Okay, so this method we say that it is the time taken to store the charge or to fully charge the capacitor depends upon the capacitance of that. It means capacity. If it would have more capacity, it would take more time to fill it up. It is just like a drum, barrel, water barrel. If it would be of smaller capacity, we can fill it quickly. But if its capacity is more, we have to fill it more. Okay. Similarly, when you remove the battery and you just consider it that mean what would happen to the charge stored on the capacitor. So you will have the current like this. Initially there was a huge current over here. Check this one out. Huge current mean because this plate was initially negative, so it repelled most of the electrons initially, when it repelled most of the electrons initially, it pushed basically all the electrons in the circuit. So initially current was more because electric field was there. But after that, there was an electric field developed across these plates. So due to that, the repulsion of electrons was taken place, and that's why the flow was opposed, right? When flow was opposed, the current decreases. Here current decreases, so we can say that there is a decrease in the current in this. So it takes the time. Here is very important line. After the switch close, the current will begin to at the maximum value as it and will decrease rapidly as the plates fill up.
Yeah.
Remember, when the plates are filled up,
Hello?
they do not allow over there. That makes them to be to decrease the current. So then current would remain at zero level because no more electrons are being repelled from one plate to another plate. That's why. Okay, is it clear to you? Now
Mhm.
we have the concept of charge. As you know that Q is equal to C times V. So capacitance is fixed. So it means that Q is directly proportional to V. So as the voltage is stored on the capacitor increases, likewise the charge stored on the capacitor increases. So I can say that the graph of voltages and current, sorry, voltage and charge is similar to each other, or likewise with each other. Okay,
Okay.
are you getting it?
Yes, sir.
It is direct just due to this reason. The charge and voltage are directly proportional to each other. And there is another very important thing. I mean, interesting fact over there. You know what is current? Current is equals to Q divided by T. So I can say in other words that I is equals to gradient of Q and T graph. So if it is gradient of Q and T graph, so let's say here we go. Here is the gradient maximum. It means current is maximum over here. And here is the gradient minimum decreasing. Here is the minimum gradient. So I is minimum over here. So that is why we will have this opposite graph of current. This is current. This is your charge. Is it? Is it clear to you?
Yes, sir. Oh, sir.
Yes. Now,
Uh,
yes, yes.
Oh, I think that's enough for today because I have work to do now. It's been 1 hour class.
You are tired.
No, because I have a IA due in an hour, so I'm gonna finish that.
I mean, you have a class ahead with anyone else?
Oh no, I have work to do, sir. And it's been one
Okay,
hour for
just
this
a
one.
minute, just a minute. Oh yeah, leave it 1 hour. I am going to make you clear about all this. So why you are going to complete ours? Huh?
Oh no,
Should we not
because
complete the syllabus?
oh no, oh no, because I
If you
wanted
give
to
me
just
just 10 more minutes,
okay,
over right, we are over here. So just five, 6, 7 slides are there. So if you just give me 10 more minutes, I would be able to complete it.
okay,
Okay. Okay. So I was over here that current here is, as we know that voltages across the resistor are proportional to the current. That's why if we have if we have very high resistance, right, then the voltages would be low. Here there are three graphs: low RC. I will talk about RC, then it would be very clear to you. So just keep this as a mean pending. So here we go. But when we discharge the capacitor, right, what do? Actually, we connect that capacitor with a resistor. Here if we connect the capacitor, this switch at position A, actually capacitor would be stored, mean charge. But if I connect the switch at position B, the capacitor would have a discharge. Got it?
Got it.
Right. So whatever the energy was stored in this is the charging loop and this is discharging loop. Okay. So I can say that this is when the switch is in position A, the charge is stored on the capacitor, and when the switch is at position B, the charge is discharged from the capacitor. It is lost from the capacitor. So these are two very easy ways to now, or easy ways to figure it out. Then here that okay, this is now he has placed this as position B and then remember made this capacitor as a battery. So this is the positive battery terminal, this is working as just like a negative terminal battery. So overall, what do we say? That the current is here is that point what I have included to you. This one, okay, let's make this line very clear, that as V is equal to Q by C and change in charge divided by T is your current. I mean, as I told you, the gradient of Q and T is your current. So Q by C minus R into Q by T is equal to zero, because sum of all the voltages across the loop, this is that circuit, I mean that concept, that sum of voltages would be equal to zero. So simply just don't get confused in that. You have to remember one thing, that Q divided by T is equal to Q divided by RC. So this is the concept of RC, that it negative sign shows that there is a discharging takes place. What happens that discharging takes place? So simply speaking about that, here your RC is equals to T, because it would be cancelled from this, Q and Q would be cancelled. So you can say that R and C would be equal to T. So this is the very important equation, that RC time constant. What do we call it? It is called your RC time constant. So here we go, that T is equals to your R into C. So in case of discharging, the equation will be Q is equals to Q naught into E times T by RC. This equation is given to you in your data booklet, so just use it from there. Okay. So when you are going to use that from use that equation from there, it would be very helpful for you. So from here, I can calculate that what would be the RC time constant. RC time constant is that constant in which 63% of your capacitor is discharged. Okay. So here we go. That if we write the equation in terms of charge, so Q is equals to Q naught divided into E power minus T by RC, and if in this equation, in this solution, we have calculated the RC time constant. RC time constant is basically the product of resistance and capacitance. So here we had a resistor of 10 mega ohm, 10 into 10 power 6, and capacitance was 275 into minus 6, so minus 6 plus 6 gone, so it was 2750 seconds. 2750 seconds would be taken for your capacitor to charge to 67% of that. So Q is equal to C times V. So C is given to you, V is 6 volt. So how much capacitance would be charged on this one, or how much charge would be stored? 0.0, I mean 1.65 millicoulomb into 10 is power minus 3 coulomb will be stored on that. So here is again the same equation, the worked solution. So yes, check this one out. R is this one, tau is this, and Q is this. We have calculated how much charge will store on that capacitor. So the question is now very important thing, by using this equation, what to do? Find the charge on the plates exactly one time constant after discharge begins. So one time constant means your T would be equals to RC. So when your T would be equals to RC, you will put this equation, Q is equals to Q naught into E power minus T by T. So here Q is 0.060165 and divided by E, it would be equals to 0.00607 coulomb will be the charge store on this. So this is basically 37% of the original charge. So simply speaking, here we go, here we can define that the RC time constant in discharging is in which 37% charge is left over, or 63% charge has been discharged. That time is called your RC time constant. Okay,
Yeah.
that is, you have to remember. So that was basically, that is also in the same case of voltages. If we have the equation of voltage, if we want to use the equation of voltage, V is equal to V naught e power minus t divided by RC. So it is again very simple to understand that V is equal to V naught into E times minus t by RC. So uh, note that this is the same answer as we got on the previous slide. We have calculated that, and then we can consider this all, that half time, actually, this is just like your half life.
Yeah.
Half time, half time of discharge is equals to RC times natural log of 2. Just you have to recall this equation. RC is basically tau, okay, and that is the half life of your capacitor. So your capacitor would be 0.693 times RC is the half life of your capacitor. Okay, here we have calculated this all, that T is equal to this, and time of half life is 2500 second. We have calculated that. Sorry, for the time for discharging was 2500 second. So the time for half life would be this much time. It means half of the capacitor would be discharged in this time, and then we can calculate any of the required value. For example, here we go, that we are asked that what would be the resistance required then if we want to discharge the capacitor in its half of the life. So we can get this number as 13.1 mega. So this was all about your capacitor 13.3. I hope that you have got it. Although this was a
Yeah.
very long lesson, I believe that how much time it took, you have been, destroyed mentally. But I believe that it was my responsibility to do this. So I revised it. I have sent you the notes, and believe that. I believe this thing, that you will work on it, and meanwhile you will not get any